Thank you everyone for attending this talk. This is Joy Work with Badikasi, Ravi Kumar, Rasmas Pa, and Amar Sinha. We study the distributed analytics setting where there are end users and the analyzer. Each user I receive as an input xi, and it can produce a message yi. These messages are then sent to the analyzer, who use them to compute an estimate of some function f on the input. We focus our attention on the real summation problem, where each xi is assumed to be some real number between 0 and 1, and we would like to compute the estimate of their sum. We would like to do this while respecting the user's privacy. Specifically, we use the differential privacy notion of Dwork et al., which requires that if we change a single user's input, then the output distribution shouldn't change too much. So far, this definition is somewhat underdefined because we haven't specified the scope of our algorithm and specifically what we consider to be the output of our algorithm. And choosing different scope for the algorithm will result in different models of differential privacy. On the one end, there is the central model or the curator model of differential privacy, which consider the entire protocol to be a single algorithm and just want to protect the output estimate. This model is great in terms of accuracy. It's known that for epsilon DP algorithm, one can achieve an error of 1 over epsilon, which is very small given that we consider epsilon to be some small constant. However, this also requires a lot of trust because, for example, the analyzer may even see the user's raw input in this model. And this might not be desirable in distributed settings. And this leads to a different model of differential privacy, which stands at the other extreme, called the local model. This model thinks of each user's randomizer as the algorithm and require that each message that the user sends to the analyzer has to be differentially private. This model is great in terms of trust because what leaves the user's device is already differentially private. However, we also have to pay in terms of accuracy loss. Specifically, it's known that the best possible algorithm in this model achieves an error guarantee of square root of n, which is quite a large gap compared to the 1 over epsilon in the central model. This large gap leads researchers to try to come up with middle ground model, which can achieve weak trust of the local model while also achieving high accuracy of the central model. One such model that is the focus of our work is the so-called shuffled model. The setting of this model is very similar to before, but instead of the messages being sent directly to the analyzer, they are first sent through the shuffler, who shuffles all these messages before forwarding them to the analyzer. The requirement here is that these shuffled messages have to be differentially private, or equivalently, that the multi-set of messages sent by all the users have to be differentially private. This model has been studied under different names in different community, including the anonymous model, the encode shuffle and analyze architecture, or just the shuffle model. Now that we have described the model, let us get back to our real summation problem. As stated earlier, in the central and local DP, the tithe error is 1 over epsilon and roughly square root n, respectively. In the shuffled model, Ballet et al. Show that the error is n to the 1/6. This is indeed much better than the local model, but it's still not quite as good as the central model. Fortunately, Ballet et al.'s lower bound only holds against single message algorithm, and this leads to a study of the slightly relaxation of the previous model, which we can call the multi-message shuffle model. In this setting, each user can send multiple messages, and all these messages are shuffled together before being sent to the analyzer. And the requirement is the same as before, that these shuffled messages have to be differentially private. So in this multi-message setting, indeed, we can overcome the lower bound of n to the 1/6 from Ballet et al. Specifically, Xu et al. Shows that an error of log of 1 over delta over epsilon is possible. Again, this is close to the central DP up to the log 1 over delta factor. And this log 1 over delta factor was later removed simultaneously by two papers of Barley et al. And Garcia et al., who shows that one can achieve the same asymptotic error as in the central model in this multi-message shuffle model. However, their algorithm still requires each user to send many messages. Specifically, the number of messages grows as log of 1 over delta over log n. So if delta is subpolynomial in n, then this will be super constant. In this work, we show that this super constant number of messages is not necessary. In fact, we give an algorithm that can achieve near central accuracy, while each user only send in expectation 1 plus order of log 1 over delta over square root n messages. So for a very large range of delta, this second term is just little or 1. So the number of messages sent per user is just 1 plus little or 1 in expectation. Finally, we should note here that all of the shuffle DP results we discussed so far are for the case where delta is greater than 0. When delta is equal 0 in the PLDP setting, we also wrote a paper last year that give an algorithm in this setting. However, the error is still not exactly 1 over epsilon, and it remains an interesting open question whether the error there can be brought down to 1 over epsilon. All right, with this result in mind, let us move on to describe the high-level ideas of our algorithm. So first, it will be much simpler to deal with the discrete setting instead of the continuous, the real number setting that we are in. And thankfully, this was already done in previous work of Barley et al. Specifically, we will consider the delta summation problem, where this means that each xi is assumed to belong to 0, 1, and so on to delta, where delta is a positive integer. Barley et al. Shows a reduction from the real summation to this delta summation problem, where each xi is replaced by randomly rounding delta times xi. And they show that it suffices to find a protocol with error delta over epsilon for delta summation when delta is equal to order of square root n over epsilon. In other words, we can focus our attention to this delta summation problem. And specifically, what we can show here is an epsilon delta shuffle DP protocol for delta summation problem, where each user sends 1 plus order of delta times log of 1 over delta over n messages in expectation, and each message is of log delta bits. And when plugging in big delta equals to square root n, this indeed gives the result that we discussed in the previous slide. Okay, so from now on, we will focus on this delta summation problem. To understand our ideas, we have to first go back to the algorithm for the central model for this delta summation problem. So the most basic algorithm in the central model is the so-called noise addition algorithm, where the analyzer just receives the raw input, sum them up, and then add to it some noise drawn from some distribution D. And for the purpose of this presentation, we might write the distribution in the sum itself just for simplicity. For the delta summation problem, the noise distribution used here is the so-called discrete Laplace or the symmetric geometric distribution. This distribution is parameterized by some number b greater than 0, and its probability mass is going down by a factor of e to the minus b when we are moving one step further away from 0. When adding this discrete Laplace noise with parameter delta over epsilon, the algorithm is epsilon dp in the central model and achieves the error of delta over epsilon, which is indeed the error that we want, but we want it in the shuffle model. So how do we implement such an algorithm in the shuffle model? To do this, we have to introduce the concept of infinitely divisible distribution. At a high level, we would like to distribute the noise among all the end users. And the concept of infinitely divisible is precisely this. Specifically, a distribution D is said to be infinitely divisible if for every positive integer n, there exists a distribution which we denote by D divided by n here, such that if we take the sum of n IID samples drawn from D divided by n, then this sum is distributed as the original distribution D. And there are multiple famous examples of this. For example, the Poisson distribution obeys this rule, the negative binomial distribution as well. And most importantly, the discrete Laplace distribution also satisfies this rule as well, because the discrete Laplace distribution can be written as a difference of two independent negative binomial distribution. So our algorithm builds on the idea from our previous work in ICML last year, where we gave a similar result in compared to this paper, except that it only worked for the case of binary summation, where the delta is equal to 1. In other words, each xi is either 0 or 1. So let's first see what a direct adaptation of that paper would mean for the delta summation for delta greater than 1. And here I will describe a slightly inaccurate adaptation just for simplicity of presentation. So in addition to the number of users n, the algorithm is also parameterized by an infinitely divisible distribution D on non-negative integers. Each user on input x will output messages that are either +1 or -1. And the number of +1 messages and -1 messages are computed as follows. So first, the user will sample two IID random variables, C and C minus, from D over N. Then it will send C plus X messages +1 and C minus messages -1. As for the analyzer, it just looks at all the messages, sum them up, and that's the estimate that it outputs. So that's the entire algorithm. Let us now see the analysis of this algorithm, and we will here focus on the utility analysis. So first, notice that we're only sending +1 and -1 messages. So from the analyzer viewpoint, it only sees the number of +1 and the number of -1. And from infinite divisibility of distribution D, the number of +1 is simply just the sum of x1 to xn, the true answer, plus a noise independently drawn from D. And the number -1 is simply another independent random variable drawn from D. For the utility, our analyzer's estimate is just the sum of the messages. So this is exactly the sum of xi plus a random variable drawn from D minus another independent random variable drawn from D. And as stated earlier, discrete Laplace distribution can be written as a difference of independent negative binomial. So if we select D to be this negative binomial distribution with appropriate parameters, then we have that this D minus D term is distributed as a discrete Laplace of parameter epsilon over n. So this means that this algorithm has exactly the same utility as the discrete Laplace mechanism in the central DP setting. So this is great, except that we are actually sending a large number of messages. Why is that? That's because each user sends Z plus X number of messages +1. But our X here can be from 0 to delta, unlike in the previous work where the X can be just 0 or 1. And this means, for example, that if X is equals to delta, this user will send at least delta messages. And this is bad because recall that our delta is pretty large. It can be as large as square root of n. All right, so let's now think about how can we avoid this large number of messages. The solution here seems pretty obvious. Currently, we are sending X messages of +1. In other words, we are encoding X in unary. So why don't we just encode in binary, meaning that just send one message equals to X. So we can do this, and the rest of the algorithm remains exactly the same as before. Utility-wise, this is great. Again, this achieves utility similar to the discrete Laplace in the central model. Unfortunately, it's blatantly violating privacy. The reason is that all the noise parts are in the +1 and -1 messages. In other words, by looking at the number of messages equals to, say, 2, then we know exactly the number of users that have input equals to 2. And this is bad. So how should we fix this? Since the utility is already good, we want to add more messages while not messing the utility up. This is achieved by adding zero-sum noise. In other words, we will be sending additional messages whose sum is equal to 0. This will not mess up our utility, but it will help us with privacy. Now, there are multiple ways to implement this strategy. The way we do it in this paper, which will later on help us with our privacy analysis, is as follows. For certain multiset S, which is a subset of minus delta to delta, whose sum is equal to 0, we select some appropriate infinitely divisible distribution ds for it. The user will then sample zs from this distribution ds divided by n, and then send zs copies of each element of s. So this means that the sum will be equal to 0 as desired. Just as an example, suppose that s is equals to the multiset +1, +1, and -2. Then the user will randomly select zs from an appropriate distribution. And then suppose cs is 2, it will send +1, +1, -2, and then again +1, +1, -2 for a total of 6 additional messages. And these messages sum up to 0. So what is the intuition here? The intuition here is that adding a lot of zero-sum noise should drown out any useful information except for the sum of all the messages. And as we stated earlier, the sum of all the messages is just the sum of xi plus the discrete Laplace noise. So it's already dp. So that's the high-level intuition. But to analyze this formally is pretty challenging. To understand this challenge, let's consider the view of the analyzer. Now, the analyzer will see the number of messages that are equals to delta, that are equals to delta -1, and so on and so forth, to the number of messages that are equals to minus delta. Now, each of these terms both depend on the input and also depend on multiple noises. Moreover, each noise also appears in many of these terms. For example, in the case of s equals +1, +1, -2, the noise cs appears in both the number of +1 messages and the number of -2 messages. And this makes the privacy analysis very challenging. The way we overcome this is to do a change of basis so that we are in a new basis in which each coordinate has independent noise. And once this is the case, we can analyze the algorithm using standard techniques that have already been used, for example, in histogram problems. Okay, so that's all the technical aspect of our work that I will be able to talk about in this short talk. Now, let me conclude here. We gave an epsilon delta shuffle DP protocol for real summation, whose error is almost the same as the central DP Laplace mechanism. And the expected number of messages is just 1 plus 0 or 1 for a very large range of delta. Our protocol also implies a protocol for aggregating vectors that are one sparse, meaning that it's non-zero in just a single coordinate, where the dimension is much smaller than n. In terms of open question, one open question here is whether we can push the expected number of messages further. For example, we can ask, can we get the number of messages to be less than or equals to 1 in expectation. Another interesting open question is that in the central DP setting, it's known that Laplace is not optimal for very large epsilon. And in that regime, the error can be pushed down to something like exponential in the minus of the order of epsilon instead of 1 over epsilon achieved by Laplace. This can be done via the so-called staircase mechanism. Is an interesting open question whether this kind of error can also be achieved in the shuffle model. And with that, thank you all very much for your attention. Thank you.